Okay, in section 4.3, we're going to talk about linear independence and basis. Okay, so we're talking about vector spaces. Now, linear independence and basis are two things that we have talked about before, but we can expand these definitions to look at other vector spaces besides just the real numbers. So, for example, if I have the space P2, okay, well, we know what P2 is. P2 is all polynomials of degree 2 or less. Okay, so all polynomials of degree 2 or less. So a form of a polynomial in P2 looks something like AT squared plus BT plus C. Okay. So it's logical then to think about the vectors in P2 looking like ABC. Okay. They have an A component, a B component, and a C component. So naturally we could set up a basis for P2, call our basis B. And this basis B would include the A vector, A0, 0, 0, B0, and then 0, 0, C. Okay, so if I'm looking at this, my basis B in terms of the vector representation looks like that, but really my vectors correspond to the polynomials. In this case, this would be a t squared polynomial, a t polynomial, and then a constant polynomial, which is just 1. Okay, so I could represent that basis that way. Okay, so this would be the standard basis for P2. Okay, this would be the standard basis because it's the one that's analogous to the standard basis for R3, right? If I think about R3, the standard basis is the identity vectors, E1, E2, and E3. And remember what the identity vectors are? They would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so that would be your identity basis. Okay, so that's P2. Now, we could also think about larger spaces, right? I could go to P5, let's say. So a basis for P5, well, we're going to have one for the highest power, that's t to the 5th, t to the 4th, t cubed, t squared, t, and then a constant 1. So notice there are 6 vectors, and they're vectors even though they're polynomials, because we're thinking of these polynomials as being a part of a vector space. Okay, so I have 6 vectors here that make up this basis. So P5 is 6-dimensional. Remember that the dimension is the number of vectors in a basis. So I have 6 here, P5 is 6-dimensional. Just like if I look back, P2 had 3 basis vectors, so it was analogous to R3, right? The ones down the diagonals, okay? Similarly, if I have a matrix space, let's say M 3 by 3, okay? And a 3 by 3 matrix has 9 entries. So this would be 9-dimensional, okay? And you think about what your basis vectors would look like here. You would have one where you had 1 in the upper left. Okay, then you would have another one where you had 1 in the upper center. They should all be 3 by 3 matrices. And this would continue indefinitely, right? I could do the whole top row here, and then we'll just say it continues indefinitely. I'm not going to write out 9 3 by 3 matrices here, but you could have 9 3 by 3 matrices with a 1 in each position to get your standard basis for a matrix space. Okay? You can also think about taking that matrix space and sort of expanding or unfolding that vector. So think about writing this as a vector in R9. So this is going to be analogous. The word is isomorphic. You don't have to remember that word. It's going to be analogous or isomorphic to R9 because I have 9 possible coordinates. So naturally then M 2 by 2 would have 4. Okay, M 2 by 3 has 6. So when you're trying to figure out the dimension on a matrix space or possibly the number of basis vectors, you're really just multiplying the dimensions. 3 by 3 gets you 9, 2 by 3 gets you 6, 2 by 2 gets you 4. Okay, for a polynomial, right, we have one more than we do degrees here because I'm going to have that constant vector at the end. So P5 has 6, P22 would have 23 such basis vectors, P27 would have 28, okay? one more there for polynomials, okay? So remember, to be a basis, okay, to be a basis, you must have a linearly independent set, and the set must span the space. Okay, so a basis for H has a linearly independent set, and that set spans H, or whatever the name of your space is. Okay, that's what you have to have. Okay, and you can think about unfolding these into different spaces, things like that. Okay, now if you can find a spanning set, then you know you have a basis, and you know you have the dimension. So that's what we've been doing along the way here, right? I can have a spanning set for P5, looks like that. I can also have spanning sets for subspaces, okay? So let's look at another one here. Let's look at P2, where I have the vectors P1 is equal to 2, P2 is equal to T. Notice these are polynomials, so I'm writing them as of T. And P3 is equal to 6 minus 2t. Okay, so P2 subset has vectors P1, P2, and P3. Okay, and I forgot to name my subset. We'll call this subset H. So we want to find a basis for H. Okay, so as I'm looking at these three vectors here, I have a corresponding representation for these three vectors in standard vector form, or R3 vectored form. So 0, 0, 2, 0, 1, 0. And this one then would be 0, negative 2, and 6. Okay. So as I'm looking here, I can make this third vector a linear combination of the first two. Okay, to get 6, I need 3 copies of P1. To get negative 2t, I just need negative 2 copies of P2, and that's going to equal P3. Okay, so I have a dependence relationship here. And if I have a dependence relationship, I know I don't have independent vectors. Okay, so P3 is not independent of P1 and P2. Now, as I look at P1 and P2, they are independent. For that matter, if I look at P1 and P3, they're independent. If I look at P2 and P3, they're independent, because there's no multiple that's going to get me one of the other vectors. But if I put these two together, I can get the third vector with the right combination. So I can find a basis for H. I can actually find 3 different bases for H. Okay, first basis is going to be V1, V2. A second possible choice is going to be V2, V3. And then a third possible choice is going to be V1, V3. So those all work as possible bases. These are distinct bases, okay? This is one choice, this is another choice, and this is another choice. They're not all a basis together. V1, V2, V3 together does not make a basis, okay? Now, notice that the basis has 2 vectors in it, but H has infinitely many vectors because it's a span of 2 vectors, so it would make a plane. And you could find an appropriate relationship there, okay? Now, we also have bases for some sets we've been looking at. We have basis for a null space, a column space, or a row space, okay? Now, a basis for a null space, a column space, or a row space is more or less what we've already done. So if I take a matrix, okay, so basis for a null space, column space, or row space, let's take a matrix A. Okay, and my matrix A looks like 1, 0, negative 2, negative 2. On the first row, 0, 1, 1, 4 on the second row. And then the third row, 3, negative 1, negative 7, and 3. Okay, so naturally I'm going to row reduce that matrix. Okay, so put in your matrix here: 1, 0, negative 2, 0, 1, 1, 4. Third row, 3, -1, -7, and 3. I row reduce that matrix, and we get the following result: 1, 0, -2, 0, 0, 1, 1, 0, 0, 0, 0, 1. So notice where the independent columns are. Okay, I have my pivots here in columns 1, 2, and 4. So column A is going to be equal to the span of its basis, which is going to be the first those three pivot columns of the original matrix A. Okay. Now, it's important to recognize that the columns of B, your row reduced matrix, do not necessarily form a basis for A. Okay. However, in this case, my vectors here are in R3, and I have 3 of them. So this span is actually equal to all of R3 because I have that matching dimension case. The vectors are in R3, and I have 3 vectors. So it goes to R3. If I'm in R4 and I have 4 vectors, it's all of R4. Okay. So actually, these 3 columns here for B, because they also, or the reduced part of A, not B, the reduced version of A actually would also span the same space. But in general, we cannot expect that. That only works if we have that case where those dimensions match up. Okay. Now for the row space, for the column, try that again. For the null space, okay, we set up our homogeneous equation here. So I'm going to have that x1 is equal to 2x3. x2 is equal to negative x3. x3 is a free variable. And x4 is always 0. Okay, so I have a vector here then that is 2, -1, 1, 0. So that is my basis for my null space. Okay, it's the span of just that one vector, 2, -1, 1, 0. So any vector in the null space is going to need to be a multiple of this vector. Okay, now the null space is inside of R4 because I have 4 columns, but the null space is not all of R4 because I only have one basis vector. I only have one free variable. Okay, now the row space we haven't talked as much about because it's a little less important, to be perfectly honest. So when I'm looking at the row space, I'm looking for where the pivot rows are. Okay, so I have 3 pivot rows here. Okay, so we would say the row space is equal to the span of those rows. Okay, and it looks weird because they're row vectors here. So this is 1, 0, -2, 0. That's my first one. My second one then is going to be 0, 1, 1, 0. And my third one is going to be 0, 0, 0, 1. I know it looks weird and I can't hardly fit it on my camera. Like I said, it's actually a little less important, but it does come up every now and then. So the row space has those row vectors. Okay. And each of the independent rows or each of the pivot rows of the reduced matrix. So you do go to the reduced matrix for the row space of A. Okay. Now we can also have systems that look a little different. Okay. So let's try another, or not system, let's try another vector space. So my vector space H is contained within P3. Okay. But it only has the vector P1 of T is equal to 6 minus T squared plus T cubed. Okay, 6 minus T squared plus T cubed. That's my only vector. Okay, that's my only equation. So when I'm looking for the column space of H, okay, I'm breaking down the pieces of this vector. So the column space of H then would have, and you can go in either order. So I've been going from the highest power down to the lowest power. So I'll continue that pattern here, 0, 0, 0, 6, as long as you define your variables accordingly. So as a vector, then I would have 0, -1, 0, 0. And then the third one would be T cubed, which would be 1, 0, 0, 0. Okay, so that's the corresponding representation in R4. Remember R4 because it's P3. But you could also do this with, and this should say span here. Sorry. It's the span of those vectors with the pieces. So I've got 6, I've got -T squared, and I've got T cubed. That's going to correspond to my column space. Okay. Now my null space, I'm setting this equal 0, right, to do the null space. So imagine setting that equal 0 then. Solve for one of your variables. So I'm going to solve for t cubed because it's positive. Okay. So I have the equation then t cubed is equal to positive t squared minus 6. Okay. Now, my other two, because I only have the one equation, my other two variables, or my other three variables, I should say, are free. T squared is equal to t squared. T is equal to t. In this case, negative 6 is not negative 6. 1 is equal to 1, right? Those are all three variables. All free variables. There we go. Free variables. So as I look at this, my null space is going to have three vectors in it, which means I made a mistake in my column space. Sorry, I was getting ahead of myself here. So my null space is going to have three vectors in it, right? I have a vector for the constant. Okay, that's going to be negative 6 in the first one here, 0, 0, and 1. The second one, I'm going to have 1t squared, 1t squared again, 0 and 0. Again, I'm writing the coefficients here. So I had negative 6 with a constant 1. I have t squared with t squared free. I don't have any t squareds in the others. The third one, I have no copies of t in that equation. I just have the one free variable t. And then I'm done because I just have three free variables. Okay. So there's my three variables that are the null space. And I was getting ahead of myself. My span here should just be the span of that one equation I'm given. I want to get rid of those columns, or those commas, I should say. Span here should be just that one vector. And so as a vector, that would look like one copy of t squared, negative one copy of one copy of t cubed, negative one copy of t squared, no t's, and 6 for the constant term. Okay. So here would be my null space. Here would be my column space. Remember that our rank theorem tells us that these should add up to 4 because P3, remember we said is like R4, and R4 has 4 dimensions. Okay, so those dimensions should add up. Okay, let me do another one there so that I won't mess one up. Okay, so I'm going to have another one here that is A plus 6B minus 2C equals 0. This is my space H. Okay, so for my space H here, that's what I have. So then the column space, I just have one equation. That's going to be, and that should be H, not A. It's going to be the span of this vector where I have one copy of A, 6 copies of B, and negative 2 copies of C. Okay, for the null space, again, you write this as a homogeneous equation. So I have A is equal to negative 6B plus 2C with B and C as free variables. So one equation, 3 variables, you're going to have 2 of them left over, 2 of them that are free. So your null space of H is going to be the span of my A vector here, which is going to have negative 6 copies of B. Sorry, let me try that again. A is a basic variable, so I'm going to B. Okay, I've got negative 6 copies in the first equation, 1 copy in the second equation, and nobody in the third. In my second, I've got 2 copies in the first equation, nobody in the second equation, and 1 copy in the third. Okay, so write that equation to get you the null space. Okay, set it equals 0. Your other variables are going to be free. Okay, now there are other bases you could do here because you could establish B as your basic variable and make A and C free. Okay, but at any rate, your column space vector is going to have to be the same because it's that relationship amongst those variables. Okay. Now, the other thing to be cautious of is maybe they give you a system or a subspace or a potential subspace that involves some trig functions. Okay, you do have to be careful. So let's say, for example, I've got sine t, tangent t, and sine t, cosine t. I'll do one more that's going to be sine of 2t. Okay, so I got all these vectors, 4 different vectors. And the question is, are they independent? You know, what's going on here? Well, it's important to notice that sine t and sine 2t have an identity that relates to them. So if you have sine 2t, that is the same thing as 2 sine t cosine t. So what that means is this fourth vector is actually a multiple of this vector. Okay? So let's label these vectors v1, v2, v3, and v4. Okay, notice that 2 times v3 is the left side of this identity. 2 times, let me try that again. I know where I'm headed. I've got v4 is the left side of this identity, sine 2t, and 2 times v3 is the right side. So this is clearly a multiple. So your basis vectors then would just be those 3. Okay, v4 would not be a basis vector. So this space would have only 3 dimensions. Okay, so be mindful of that identity cropping up to make things maybe a little deceptive. Okay, because there's not any multiple of sine that gets us tangent. There's not any multiple of sine that gets us sine times cosine, right? Cosine is not a constant number. Okay, if one of these vectors was just 2 tangent t, that's clearly a multiple. So you're always looking for vectors that are multiples of another vector. Okay. All right, so let's look at a couple more with polynomial spaces here. So if I have 4 minus p, 2 plus p squared, and 6 minus p plus p squared. Okay, so as I look at this, I can actually make this a subspace of a lot of spaces, but I'm going to make it a subspace of p2 because that's the smallest one. I could actually go up to p3. I just have all zeros for the third degree, right? So 3 vectors. I could have all 3 vectors be bases. So we're looking at this to say, okay, are any of these multiples of each other? Okay. Well, I have a hunch they might be because 4 plus 2 is going to give me 6. Okay, so if I look here, v1 and v2, if I add them together, I get 6 minus p plus p squared. 4 plus 2 is 6. Minus p is still there. P squared is still there. So that is exactly v3. So these are multiples of each other. So my basis for h, right, call this h, it's a subset of P2. And in fact, it is a subspace of P2 because I have a spanning set. Okay, my basis B is actually just going to be the span of V1 and V2 because V3 is a linear multiple of the other two. And again, like the other example, I could do V1 and V3. I could do V2 and V3. Okay. Now the homework may ask you to put in what V1 is. You know, you have to put in 4 minus p squared here. You have to put in 2 plus 4 minus p and 2 plus p squared. Okay, pay attention to the way the question's asked. Now, if you're not sure if they're a multiple, you can always look at them as vectors, as a matrix. Okay, so I'm going to take this first one. I'm going to have no copies of p squared, -1 and 4. Okay, second one, I'm going to have 1 copy of p squared, no p's and 2. The third one, I'm going to have 1 copy of p squared, -1 copy of p, and 6. Okay, and I can row reduce that matrix. Okay, so take your calculator or your favorite row reduction method. You know, you can use websites, so forth. There's lots of ways to row reduce. You can use row operations. You know, switch the rows around as needed. Row reduce that, and you should get 1, 0, 1, 0, 1, 1, and then all zeros along the bottom row. Okay. So as I look at this, the first 2 are independent. So I use the first 2 in my basis. Okay. That tells me which ones are independent, just like it does when I'm in the real numbers. When I'm in R3 or R4, whatever it might be. Okay. You're always looking for those linear combinations. Okay. Sometimes you have to use the matrix. Sometimes you can just eyeball it like we did here. 4 plus 2 got a 6. And then the other 2 are still there. Okay. So sometimes it's a little easier to spot than others. Okay. So let's look at another one here, the same type. So h is the span of these vectors p plus 2, -6 minus p plus p squared, and 2p plus p squared. Okay, again, spotting exactly what might relate here may be a little challenging, so you can always set up the matrix. But I see that 0, I don't have a constant term here in the third one. So I have 2 and -6. So the only real possibility is going to be if I have 3 copies of this one and 1 copy of this one. Because that's going to give me 6 minus 6 gets me 0. Okay, so 3 copies here gets me 3p. Doesn't match up yet, but minus p. So 3p minus p is 2p. I have no p squareds here. I have 1p squared here, so I get 2p plus p. So this is the dependence relationship. Okay, I took 3 copies of V1 and added it to V2 and got V3. Okay, so similarly, I could use that to find the null space. That tells me that this relationship, okay, is going to give me my my dependence relationship is going to give me that corresponding matrix in R3. So I have that dependence relationship, which means these two are my basis vectors. It also tells me my null space, right? I have that x1 is equal to -3x3, x2 is equal to -x3, and x3 is free. But remember what these correspond to, right? This would be, this top line is your p squareds, this middle line is your p's, and this bottom line is your constants, okay? So my constant is what's free. Okay, so I have a vector here that would be -3, -1, 1. Okay, so my basis for the null space then is the vector, which looks like a polynomial here, -3 p squared minus p plus 1. Okay, it's any multiple of that vector. So you see where I got those coefficients? That's going to give me the null space here of H, right? My column space I can do by identifying what the basis vectors are. Okay, and that gives me that. Okay, now one more thing. Make sure, look through my notes, make sure I got everything I wanted to say. Yep, I just see one more thing. So if I have two bases, okay, so H is equal to, or H has basis V1, V2, and V3. And then another space K has a basis A1, A2, and A3. Okay, so I have these bases. And A1, A2, A3, as well as V1, V2, V3 are all elements of R4. Okay, so these are all four-dimensional vectors. They're vectors that have 4 coordinates. So a basis for H plus K can only include at most 4 of these vectors. So if I put these spaces together, right, this is a hyperplane inside of R4 because it has 3 basis vectors. My 2 got absorbed into my comma there. Right? Hyperplane, 3 basis vectors. Okay, plane for 2 basis vectors and a line for 1 basis vector. Okay, so each of those relate in that way. But if I put them together, if I put H and K together, I have these 2 hyperplanes that are interacting or overlapping in some way. Okay, and when they overlap, the biggest they can be is R4 because that's where all these vectors are. Okay, so you have to figure out, I know all 3 of these are independent. I also know all 3 of these are independent because they're a basis, right? That's the definition of a basis. But if I can find one of these that's linearly independent when put with one of these, or vice versa. So I can say, okay, I'm going to start with V's and check the A's one at a time. So take your matrix, right? Augment it, V1, V2, V3. Put that with A1. Okay, and if it's independent, then you're good to go. If it's not, if you get inconsistency or a dependence relationship, then you know you have to check A2. Okay, repeat the process with A2. If that one works out, you get all ones, right? That's going to be A3 next. If it doesn't work out, you go to A3. If it doesn't work out for any of them, then you can just pick the one set. That means there's not an appropriate relationship. But you can only have as many vectors as you have degrees here. So if it's R5, you could only have 5 vectors. If it's R3, you could only have 3, in which case you'd know that these were distinct. okay? Here I told you they were a basis, but you might not know that they're a basis. You might just know that they're a subspace, in which case you have to figure out if any of them are independent or dependent of each other, okay? So if H doesn't have a basis that, it just has these vectors that are define your space, you have to make sure they're independent of each other, okay? So your H plus K can only have as many vectors for a basis as you do degrees in the space. So if it was P5, the most you could have is 6. If it was M2 by 2, the most you could have is 4. So remember, we have 3 kind of setup spaces that we can make analogous or isomorphic. Again, you don't have to remember isomorphic, but we can make those analogous or isomorphic to the real numbers, because we're really familiar with how the real numbers, the Cartesian plane, and the like works. Okay, so that gets you started on 4.3. Let me double check before I say it. Our next section is 4.4. Okay, 4.4, where we're going to deal with coordinate systems. We've already touched a little bit on the coordinate systems, but we're going to flesh that out just a little bit further. And look at it in terms of a vector space, because now we can take our new spaces, our P's and our M's, and we can also coordinatize them. All right, so I'll see you in the next video. Make sure you're staying on top of your homework assignments, quizzes, tests. Again, please let me know if there is anything I can do to assist you or answer any questions about the course format, and I'll talk to you in our next video.